Hello, and welcome to this video about algorithms basics. It's going to be a relatively short video, and it's not going to have a lot of actual code. It's more gonna talk about algorithms and sort of set you up for some of the future lectures, where I'm going to show you more actual algorithms and how to code them. So yeah, we're going to talk a bit about algorithms. What are they? How do we talk about them? Write them up, and we're going to talk about them using pseudocode, which is sort of something you can use to make an algorithm recipe without writing actual code. So it's something you can understand across programming language. Then we're going to talk about algorithmic complexity, which relates to how many number of operations do your algorithm use, which is very related but not the exact same as sort of how slow is your algorithm or how fast is it. Less complexity is better if you can get the same result generally. And yeah, then I'm just going to show you an example of how Python sort of does multiplication, and talk about this complexity stuff and pseudocode. So this lecture mostly sets you up for future lectures. So let's dig into it. So what is an algorithm? So a technical definition is an unambiguous specification of how to solve a class of problems. A more like layman's term is it's a recipe. It's sort of telling you how you should solve a problem in a very structured and well-defined way. And you can, like, cooking recipe is a very good analog. So if you have a cooking recipe, it's gonna tell you, the human, how to bake a cake with a like set of instructions. Do this, then do this, then do this, and then you can bake the cake just by looking at the recipe. Basically, of course, there's something in the implementation, and there's a translation of saying mix flour, sugar, and eggs, and maybe if you never baked before, then you don't know that you should put it in a bowl first or something. And that's sort of where you get to the actual implementation, writing the actual code. So having a recipe or having an algorithm doesn't necessarily mean that you can write the actual code. You also need to know the language and programming. But if you don't have the recipe, then you don't know how to solve the problem at all. And when you think about algorithmic problems, it can be something we're going to talk a lot about: how to sort lists and how to search for different variables inside a list. But it can really be any kind of computational problem that you're having that you have to solve. Multiplication is technically also done by an algorithm, which I'll show you later. So what are the properties of a successful algorithm? It needs to have an unambiguous termination criteria. This is basically just to make sure that the algorithm doesn't run forever. It sort of needs to know when it's done and when it has solved the problem. Typically it's not as important when programming Python, but if you want an algorithm, you want a predefined set of inputs and a predefined set of outputs. So you sort of say, okay, I have a problem, given some input, a list or some numbers or anything, then I want this output, which is my answer to the problem. You want guaranteed finite runtime. This sort of comes back to the unambiguous termination criteria, but it also sort of, you want to ensure that you either reach the termination criteria or that you can solve, or the Python, that your algorithm knows it can solve the problem. And then of course you want the correct result out of it. A simple example is finding the maximum value in a list of numbers. And here we assume that the list of numbers are all positive numbers, because that makes it easier. So a list L, a positive number, and the output should be one number, the maximum value of all the elements, and then you can have the algorithm here. And this is one way to solve this problem. And this is sort of pseudo code, so it's telling you exactly what your computer should do, but in human words. You should define a variable called maxL and set that to 0, and then you should loop through all the elements in the list and compare each element to maxL. And if the element is larger than maxL, then you override maxL and set that to x. And once you've done that for all the elements in the list, then you know that the number that you have defined as maxL is now the largest number in the list. And it's written sort of in steps, but what you're doing is basically you have this list, and then you sort of keep having a number in your head saying that this is the largest number I've found so far, and then you check all the elements in the list and see if there is a larger number, and then you say, okay, now this is the larger number that I found so far. Then you move along, now this is the largest number found so far, and sort of that's just how you do it. I think that's how most people would do it in their head too, if they have a list of numbers. I'm told to find the largest. Yeah, so the implementation in Python. So this was a pseudocode. It can't run, but it's very understandable. And then you can define it in Python as a function. You set maxL to 0. You loop through all the elements in the list. Then you have this if condition. If x is larger than maxL, then you update maxL and set that to x. And of course, maxL is gonna be changing all the time. Yeah, maxL is gonna be changing all the time, so it's sort of updated at each stage. So we can have an example here. I'll just write some random numbers. And then, yeah, blah blah. And then we can find the max of these random numbers. Of course, I need to run it. And then you can see that the largest number found is this. And when we check the list, it's also the largest number. And we can see sort of what is actually happening in the programming. So I just want to print each time a new number is found. Then you see you're looping through the list, each element, and then we're printing out each time we're updating maxL. So first we start out with maxL being 0, so the first number will always be larger because we're looking at positive numbers. So 12 is the first large number found. Then you're also looping through 3, 4, 4, 123, and 3, 4, 4, 3 and 4 are both smaller than 12, so no updating is done. But when you get to 123, then you found a larger number, you set maxL to that, but already on the next iteration of the loop, found an even larger number. So this is of course a very simple algorithm, but that's sort of the idea of having an algorithm. Then there's a small question then you can think about. What kind of, this is a leading question, so I'll phrase it, what kind of error might occur if L is not restricted to contain strictly positive numbers? So here we assume that L is full of positive numbers, but if there is, for example, only negative numbers, what do you think would happen? Have a think about it. If you want to think deeply, pause the video. So what would happen if L is negative? If there's only one negative number, then it doesn't matter. You're still gonna find the largest number in the list. But if L is only using negative numbers, then what's gonna happen is that this max L, which started out as 0, just keeps being 0. How you would solve this is you would use NumPy's NumPy has a value called inf, which is infinite in computer terms, and then you can just start out by having it being negative infinity, and then you sort of solve this problem, and then you still find the maximum number. Yeah. Whoop. But we don't want to do that because that's not what the argument was about. Yeah, there's a small bit of bonus info. Python and a lot of other language do something to sort of make the code run faster and avoid some of the if statements or some of the lines of codes. It tries to predict the results of these if statements, such that it doesn't have to evaluate all of the code. This is sort of a side note, but it's pretty cool that Python actually does this. So that's how the algorithm recipe works in a very simple format. You will see more complicated algorithms later, but I hope this sets you up to understand them more easily. Now we're going to talk about algorithmic complexity and big O notations. So this is one way to characterize sort of the performance of algorithm, and the way you do it is just to sort of count the number of operations needed to perform the algorithm for a given sort of measure of the length of the input argument. So typically that would be the length of a list if you're doing something on a list, but it can also be how large the number is, how many digits there are in the number, sort of whatever matters for how many operations you have to do. So for example, the find max algorithm that does n operations, where each n is the where n is the number of elements in the list, and technically it can possibly do 2 times L. So the operations counted here is just this comparison, and then you have an assignment if x is larger than max L, but that will not always happen. And you still, we'll get to that. So basically you have n operations because you're comparing each element in the list to the max L variable. And you perhaps have an assignment. But when you're counting algorithmic complexity, whether you have 1 times n or 2 times n, doesn't matter. You just say it's O(n) complexity, because it's linear, and it's sort of complexity math is very different than normal math. So you don't really care about some numbers. You care mostly about whether something is linear or whether it's quadratic or whether it's log n. You don't really care about it. Is it 5 times n or 1 times n? You kind of ignore that, and that's because if you have a lot of inputs, it matters. But the main way you compare these algorithms is through this. I think it's because it matters, but it doesn't matter that much when comparing to like the actual implementation and what kind of operations you're actually doing. So you sort of abstract away from that. Even though in the worst case you could say you have 2 times n operations here, that doesn't matter. You just say, okay, the number of operations is linear in the length of the list. And then you call it this big O n or O of n, because it's linear. So if it was constant, it was independent of input size, then you should call it O of 1. Logarithmic is O of log n. Linear we had log linear n times log n. Then you have the quadratic, the cubic, the exponential. The small bracket with cursor dimensionally is that sort of something exponential. Then it just like explodes very fast as the number of the input size increases. And yeah, there's different ways to talk about, because algorithms can of course be complex, and that complexity changes because of that. In our case, it doesn't really matter. But if you had something like an extra loop inside of here, then sort of in the worst case, then our algorithm could be n to the power of 2, maybe, if all were checked. So you have sort of, sometimes you can talk about the best case and the average case and the worst case. So the best case is sort of what's the fewest possible number of operation that can be done if we get the easiest input for a given length of size, and then you have the average case and the worst case, and these are sort of a bit abstract, and you can sometimes see people give the same algorithm different sort of complexity measures, so you shouldn't get too hung up on the exact complexity measure. And yeah, as you said, only the number of operations matter, not that type of cost. And typically you only care about the highest order. So for example, we abstracted away from the fact that you sort of have 2 times n in the worst case up here. You would also abstract away from you, for example, abstract away from this assignment operation in the end, like in the beginning, because that's just one operation, and given that we already have n operations, then you're sort of saying, okay, n is worse than 1, so we're giving it the worst order of complexity. So you wouldn't be able to have an order of complexity that's n to the power of 3 plus n to the power of 2. You just say n to the power of 3. And here you can see sort of how these evolve as the length of input increases. You can see exponential is by far the worst, and then you have the others here. And sort of complexity matters, and I think people like to talk about it because it's a bit easier to talk about. It's sort of constant across computers and programming language, but it's not the only thing that matters, and the implementation can be a lot more important sometimes. So the cost of each operation matters for fixed input size. So here in this little example, it's sort of, you set an assignment operation to be the same cost as a comparison operation, and you can also have multiplication be one operation, but in reality, as I'll show you later, multiplication actually has multiple operations inside of it because it's its own algorithm, but typically we'll count it as one when we are counting, but for other purposes you might want to count multiplication as its own operation. Then there's the thing about memory. So you might be able to save some number of operations if you store a lot of data in memory and just drag or use whatever you stored for later. But this will not necessarily increase your speed if you're using a lot of memory to store some data, because taking things in and out of memory and also matters where it is stored on the computer. This is just a little bit harder to sort of get at and think about and fix, especially in the beginning. So it's not really something you should worry about. You should just know that complexity is not the main thing but it's something that's easier to do something about. And especially if you have something that's of exponential complexity, then updating it to something like log linear will help you a lot. Yeah. Yes. Now I have a bit more of a longer example of complexity calculation. So this is a demonstration algorithm. It does 3 assignments in the beginning. These are not arguments. It takes one argument called n, and then it does a bunch of operations or calculations. So it loops through n, and then it loops through n again. So for each n, it loops through n, which means that it does this these 3 lines of codes are run n times, and then it does, for each line of code, it does 2 operations, it does multiplication, and it does assignment, which is why we have 3 to the times n to the power of 2, which are the 3 assignments, or the 3 multiplications in here, and then we have 3 times n to the power of 2 assignments. After that, it does another loop just over n. So you can see here it has first n. Yeah, okay. And the first line has n multiplications, n additions, and n assignments, and the second line it just has n assignments and n multiplications, and then it has one more assignment at the end. So the total number of operations will be the first 3 here, the 6 times n to the power of 2, then the 5 times n operations, and then the 1 assignment down here. And then you can sort of add these together. In big O notation, this will just translate like this large number, or this sort of equation will translate into n to the power of 2. Because we don't care about these, because these are of lower order, and we don't care about the 6, because it's just sort of the main thing we care about is the order of how the complexity evolves. And yeah, I also know this before, that sort of there can be multiple operations inside multiplication, but we don't count that in at this stage. Yeah. And now, so sort of I showed you how I counted all this, and now I want you to pause the video and try to count these 2 algorithms. What are the total number of operations, and what are their algorithmic complexity? Yeah. Yeah. So pause the video and try to do that. Okay. So let's have a look. Okay, so we're doing nested loops in here. Of n, we do 1 assignment. Maybe I'll write it down here. 1 assignment in the beginning, and then we're doing a 3 nested loops. So we're first doing something n times, and for each time we do that, we do it n times, and for each time we do that, we do it n times. So we're doing n to the power of 2, and then we're making this plus equal, which, I mean, it depends on how you counting it. You can count this as 1 operation, because it's sort of, it's 1 code thing, but it's technically an assignment and an addition. So I would count it maybe as 2 times n, but it doesn't really matter for the big O notation, because the big O notation just becomes n to the power of 2, no matter what. Oh, no, not 2, 3, of course, sorry, because you have 3 nested loops. Yeah, so that's the answer to the first one. In the second one, then you have 1 assignment, then you have 2 times n here, because you just have loop over n. So 2 times n, and then these two loops are the exact same. So 2 times n, so 6 times n, which means that you just have linear complexity, so O times n, O of n. So you can see that this algorithm has a lower order of complexity than this algorithm, even though you could be fooled into thinking that it's the same, because you have 3 loops here and you have 3 loops here, and then you have one sort of assignment operation stuff, or augmentation operation, but because these are nested loops, then in reality, like, Python will end up doing a lot more operations. Yeah. So that's the answer. And yeah, so the inbuilt Python functions will also have level of complexity. So if you have a list and you do an assignment, that sort of have assignment to a part of the list, or you change something of the list, or you want to slice the list, or add something to the list, or when you have NumPy arrays also, so they're not inbuilt but sort of methods, and you do matrix calculations, that will have a level of complexity. There's a comprehensive table here of sort of the inbuilt operations in Python and their level of complexity. There's also the discussion about it here, and there's also a PDF in this folder that talks about big O notation. Yeah, if you want to get more into it. For the purposes of this course, you don't really need to understand more than what we've talked about so far. I have a quick extra example of how Python does multiplication and how that matters for the complexity. So what it does is, for small numbers, it does something you could call the third grade algorithm. It's also called the standard algorithm, which is sort of how many humans do it in their heads. And then for larger numbers, then it does the Karat-Super algorithm, which I at least don't do in my head. But if I multiply large numbers, then I never do it in my head. Wait, to run this. So the demonstration is this rather large multiplication, and how you would do it. Like most human would write it up like this. You write the two numbers, multiply them together, and then you sort of take it from an end, but only multiply one of the numbers. So you start by multiplying. I think you start here. 15. Okay. So you start by saying the 3, and then you multiply to this whole number. And you even do that one step at a time. So you say 3 times 5, that's 15. You add an addition here, then you have 3 times 7, that's 21, plus the 1 that you carried over. So that's 2, but then you have to carry the 20 to the next line, and then you have 3 times 6, that's 6, but you carried the 2. So you have 8, and then you have 3 times 2, that's 6. And then you move along to multiply 10 to this number. And then because you sort of move one level up, then you have to add a 0 here, and then you do the exact same. It's pretty easy here, because you can just take the whole number. Then you have 0, and that's just all zeros. And then you have 5, but now you have to add the 3 zeros first, because you're actually multiplying 5,000. So you have the 3 zeros, and then you multiply all of these, you get all of these numbers, and then you add them together like this. And this is the way I talked about it. Was not really an algorithm, but you could write that up in pseudocode, and then that algorithm would be O of n to the power of 2, where n is the number of digits in the shortest input argument. And you can sort of see this as a nested for loop. So you loop through all the elements in here, and for each loop in the elements here, then you loop through all the elements in here. Yeah. Which by becomes n squared, because it's 2 loops. Yes, so that's the Thurberg algorithm, and that's what Python actually does for relatively small numbers, because there it's the easiest. If the number becomes sufficiently large, I don't know when it does that, but it does that at some point, then it will do the Karat-Zubas algorithm. And it's not super intuitive, but with a bit of math, it works. And for large n, then it's better. So the algorithm is n to the power of log 3. And that's better than this algorithm for large number of n's. So we have the same example as before. We want to multiply this number. Now we just call it x with this number, I. We do a little sort of rewriting, where we sort of split the number into 22 times 100 plus 75, 50 times 100 plus 13. And then we can denote these numbers just as xa and xb and xa and yb. You can write them up like this. So this is the same number, just with letters instead of numbers. And then the algorithm first computes these 3 sort of very helpful numbers called a, b, or capital A, B, and C, which is just definitions basically that we're gonna use, because then when we have this multiplication, it can be shown that the number can be that the multiplication of x and I, so the numbers that we wanted to multiply initially, can be shown to just be this capital A times 10 to the power 4, capital C times 10 to the power 2 plus b. And sort of there's a derivation if you follow this link. I'm not going to show you all, but you can sort of see intuitively A is just this number times this number, capital A. B is just this number times this number. And then sort of by definition, C times 10 to the power of 2 is sort of the cross product of these two numbers. Yeah, and it's sort of, it's not exactly, or it is exactly that, but it's sort of, it's not what you would get out when you do it first. So you have to do a bit of a rewriting, but that's just because it's easier to calculate this number than the initial number that you get out. Yeah, at least when you already calculate capital A and B, and this is how it would look like in actual numbers. So if you plug in to xi and y and xb and yb, you would get this, and this is the same as we got up here. So that's nice. Okay, cool. So thank you for watching this video. Hopefully you should now be set up to handle and understand more complex algorithms and write some of them yourself. So yeah, thank you for watching.